Alright, so next we're going to be looking at a heat exchanger. So in a heat exchanger we have an outer tube, and inside it an inner tube. So in this outer tube we have hot liquid, and it's going to be flowing in, and within the inner tube we have cold liquid, also flowing in this case. And as this liquid, as these fluids continue down the pipe, the hot liquid is going to transfer heat into the colder fluid and warming up. So we're going to be looking at specifically a differential area within this fluid with an associated differential heat, and we're going to be seeing how it transfers to the colder fluid. So first we want to write down some relationships that we know. So we know that our differential heat is going to be equal to the mass flow rate of the cold fluid times the heat capacity of the cold fluid times the differential temperature of the cold fluid. And I also forgot to mention up here on our diagram that we have position 1 and a position 2. So, alright, so then from here we can combine this term into a term C sub C. So this is our heat transfer rate. So for cold liquids or cold fluid. So we have dQ is equal to the Cc times the delta of Tc. And then we can solve for the differential temperature, and we have that the differential temperature is equal to Cc over dQ over Cc. And then we can do the same thing for our hot liquid. So we have that our dQ is equal to our negative mass flow rate of the heat. So this time it's going to be negative because the heat that's leaving this hot fluid is going to be going in. So the cold is gaining heat, whereas the hot fluid is losing heat, so we need to negate it. Times heat capacity of the hot fluid times the differential temperature of the hot fluid. And then this can also be combined into a CH. And then we can solve for D of the hot temperature, which is equal to dQ over CH. Alright, so then from here, we also know that our dQ overall is going to be our heat transfer coefficient times our delta area, or times our area, times delta T, so their change in temperature, times our differential area. So we're dealing with the differential within here, and then our change in temperature is going to be, so delta T is just equal to T2 minus T1, so 2 minus 1. Alright, so then from here, we can then take the differential of this equation, which will relate it to this I'm sorry, this is not T2 minus T1, this is temperature of the hot fluid minus the temperature of the cold fluid. So it's the heat transfer across here over this differential area with some heat transfer coefficient also included within that. So, alright. So then we have that our delta T is the change in temperature from hot to cold. Alright, so then we can take the differential of this equation, and this will connect it to what we did before, where we end up with the differential hot temperature and the differential cold temperature. So we'll have that the differential of delta T is equal to differential hot temperature minus the differential cold temperature. Alright, so then we can plug these two values into there, and we've got that, so our differential of delta T is, so temperature hot, so we got, no, I missed this negative sign when I was solving this, so our negative's now there. So it's going to be equal to negative dq over ch minus dq over cc. So we can factor out a dq, so we've got delta of, or differential over delta t is equal to negative dq times 1 over ch plus 1 over cc. So from here, we can then plug in this equation for dq into here. So we have that our d of delta t is equal to negative u delta t dA times 1 over ch plus 1 over cc. So then we can divide this delta t across to this side, and then we have two differentials on each side, and we can take the integral. So we have that d of delta t over delta t is equal to negative u times 1 over ch plus 1 over cc times differential area. So then we're going to take the integral of both sides, and we're going to take the integral from position 1 to position 2 for both. Alright, so for this side, that means that we're going to end up with the natural log of delta at t2 and delta t at position 1. And then over here we're going to have negative u times our area times 1 over ch plus 1 over cc. Okay, so then from here we want to get out what these ch and cc are. And so we sort of go back to what we were doing here. But instead of the differential this time, we just want it in general terms. So we know that our Q is going to be, so this is for the cold, so our Q is going to be heat capacity of the cold, and then temperature of the cold, which temperature of the cold, or change in temperature of the cold is going to be the liquid coming out minus the liquid coming in. So that's temperature cold out minus temperature cold in. Alright, and then same thing for our hot. We've got that our CH times our change in temperature of the hot, which is again out minus in. But again, we need to keep in mind that the sign should be the opposite of the cold stream, because this is losing heat, whereas this is gaining heat. So then that means it would be flipped within here, where we have that the temperature hot going in minus the temperature hot going out. Alright, so now we can plug these into here. So we've got that our ln of delta T2 over delta T1 is equal to negative UA. So then we want 1 over, so it's going to be 1 over CH, so that means that we're going to have this THI minus THO over Q on both, and then we're also going to do it over here, so both of them are going to be over Q, so I'm going to factor out the Q in the denominator right now. Alright, so then we have this the hot first, we've got THI minus TH out, and then this is plus T cold out minus T cold in. Alright, so then at this point we want to take these temperatures and put them in terms of our delta T1 and delta T2. So first we probably want to define what delta T1 and T2 are. And I'm going to clear us over. We can do it up here. Alright, so we're going to have that delta T1. So this is at this position is going to be the temperature of the hot going in minus the temperature of the cold going in. So that's across here. And that delta T2 is going to be the temperature of the hot going out minus the temperature of the cold going out. So that's right there. So then we can use this and plug it in down here. So we have that our natural log of delta T2 over delta T1 is going to be equal to negative UA over Q. Okay, so now we need to get these arranged in a form that makes sense with here. So we need THI minus TCI. So we got THI here and a negative TCI here. So the signs line up for that. So we got THI minus TCI. And then for the next one we need THO minus TCO. THO minus TCO. But you'll notice up here we've got a negative THO but a positive CEO or TCO. So we need to pull out a negative sign there to make the signs work. So at this point now we can plug in our T1 and T2. And I'm running out of room, so I'm just going to erase some of the stuff in the black and put it up there. So then we're going to take this to the top. So then we have natural log of, I should actually probably do that a little bit lower. I'm going to run into this right here. So, right. So our natural log of delta T2 over delta T1 equals negative U A over Q times T delta T1, so we'll place this with delta T1 minus delta T2. Alright, so we can solve for our heat. So we've got that our heat is equal to negative U A times delta T1 minus delta T2, and that is going to be over the natural log of delta T2 over delta T1. And we can also then put this negative sign inside of the parentheses, so we'll just flip this around. It's going to be delta T2 minus delta T1. So then at this point, you might notice that this portion right here with the T2s and the T1s, that is actually a logarithmic mean. So logarithmic mean is just the general form A minus B over the natural log of A over B. And so you can see that's the format that we've got here, where A is delta T2 and B is delta T1. So we can simplify that part and have that Q is equal to heat transfer coefficient times the area times the logarithmic mean of delta T. And we'll use a sub Ln to denote that. So at this point here is our equation for the heat transfer within this system. So the only question we have left is, what if our hot fluid was going in the opposite direction? If it was not co-current with the cold liquid. And you'll notice that our final equation does not have any dependence on whether things are going in or out. It only has dependence on the two position markers, so it won't matter if the flow is going in the opposite direction of each other or if they're going in the same direction. It will work either